Hello class, Dito here. The topic that I will be reviewing is kinetic theory. You can find this covered in chapters 13.9 and 10 in your physics textbook. Okay, so let's start by observing an ideal gas at the molecular level. We have a gas amount of n molecules with mass m in a rectangular container, all far apart and moving in random velocities. When they collide, both with the wall and with each other, we'll ignore any loss of kinetic energy. Figure B shows that an example of how one molecule rebounds from the wall. And as shown in figure A, we'll set one face of the rectangular container to be A and the length as L. All right, so let's get on to the more complicated stuff. We've covered this in class, but it's a good topic for review. Let's observe one molecule in the container. The molecule exerts a force on the wall, and thus the wall will exert an equal and opposite force on the molecule by Newton's third law. According to Newton's second law, the force on the molecule, F, is equal to the change in momentum, delta mv divided by t. Since it is a perfectly elastic collision, the y component of the velocity does not matter, and we can look at mv as 2mvx, since the initial momentum and the final momentum are going to be added. The molecule will make consecutive collisions with the wall, each one separated by time t, and since it travels across the container and back to L, we can use velocity is equal to distance over time to derive that time is equal to 2L over Vx, and simplify it to mv of x squared over L. Now, we have to account for all of the molecules of the gas, so we replace mv squared of x with this, which accounts for the velocities of all of the molecules, and you will get the net force on the wall and the force by finding the average of the molecules. This overbar here means average. Now, if we use Pythagorean theorem, the square of any vector is the sum of its squares, and using this on average velocity, we get this equation. Average velocity squared is equal to the added components squared, and since the movement of each molecule is random, there is no preference to going north or south or east or west, and we can set all of these components to be equal to each other. And we get that velocity squared is equal to 3 times the x component of velocity squared. Now for the sixth equation, we substitute it into the third equation, and we get force is equal to mass of one molecule over the length of the container times the number of molecules times the average velocity squared over 3. Now this is not in your reference table, and I'm sure if it is used, and I'm not sure if this is used in the AP test, but just know it to be safe. Okay. So we're going to use the force equation that we just derived to find the pressure in an ideal gas. Pressure is equal to force over area, and we just found out that F equals mass times number of molecules times the average velocity squared over 3L. Substituting that into force over area, we get nmv squared over AL times 1/3. And AL is equal to the volume of the gas, so AL gets replaced with V. This equation is also not on your reference table, so please take note of it just to be safe. The equation for kinetic energy of a gas, however, is on your reference table. It is derived from the ideal gas law, PV equals NKT, and the equation for kinetic energy and the ideal gas law agree if 2/3 of 1/2 mv squared is equal to kT. Okay. And what this does tell us is that the average translational kinetic energy of molecules in an ideal gas is directly proportional to the absolute temperature of the gas. The higher the temperature, the faster the molecules are moving on average. All right. As said earlier, the molecules will be moving at random directions and velocities, so they do not have the same speed. This graph here shows the distribution of speeds of molecules in a classroom, which is called the Maxwell distribution of speeds. It is important to note that the most probable speed located at the peak of the graph is not the root mean squared, RMS, of the graph. So as you can see here, the root mean squared is to the right of the most probable speed. As temperature increases, the graph will flatten and the peak will shift to the right. The graph shows how some molecules above a certain speed enter an activation energy margin, and the higher temperature graph will have more molecules with that activation energy. So as you can see over here, more molecules enter this margin where they will activate, whereas with a lower temperature, less molecules will activate. So anywho, I hope you enjoyed this review. Hopefully you all are doing okay at home. Please keep on self-isolating and stay well.